Order.
Okay, so welcome everybody to today's IAMP One World Mathematical Physics seminar. It's my great pleasure to introduce today's speaker, Ron Peled from Tel Aviv University. And Ron will tell us about quantitative estimates for the effect of disorder on low-dimensional lattice systems. And let me say that, as usual, the talk will be recorded and made available on YouTube. So Ron, it's a pleasure to have you here, and we're looking forward to your talk.
Okay, thank you very much, Marcello. A pleasure to be here, and thank you very much for this invitation. I'm very happy to be here in this seminar. I will tell you about my results with joint with Paul Dario, who's a postdoc at Tel Aviv, and Matan Ariel, who is now a professor in Northeastern University. And they are indeed about quantitative estimates for the effect of disorder in low-dimensional lattice systems. We will see. There are a few systems. Okay, so there is a rather general setup, and there are examples. Maybe I start with the examples. So we speak on models such as the Ising model on ZD, or the Potts model on ZD, or the Spin-O-N model on ZD. Okay, everything is on ZD. So let me talk about the general definition, but you should just have the examples in mind, really. So we are discussing statistical physics system on ZD, and we want to add disorder to them. And for the moment, I will talk about the compact state space. This will be most of the talk, but near the end of the talk, I want to tell you also about height functions when the spin variables take value in R or in Z, so they're unbounded. But for now, they're in some compact state space. Indeed, they're just minus 1, 1, just 1 up to Q, just a sphere, as you know from these models. And then we have some Hamiltonian. We will assume that it is of a finite range and finite energy and translation invariant. Actually, many of these assumptions are not needed for the results, but these are the usual settings. And then we have, as usual, the finite volume Gibbs measure. So just to remind, lambda is a finite domain. We are working in temperature T. We have boundary conditions, which we call tau, and a configuration we call sigma. And then we look at all the configurations that equal tau outside the domain, and we sample them from the Gibbs measure, the usual Gibbs measure, e to the minus 1 over temperature in the Hamiltonian. Okay, so I hope everybody in this seminar knows this setup very well. Okay, and we also allow periodic boundary conditions and the zero temperature limit, so the ground states will actually be interesting for us. Okay, so we move on. This was about lattice systems without disorder. Now I will tell you how to add disorder to them, and I will do so in a special way. Okay, so what is the disordered lattice system? Let's again look at the example first. You can consider, for instance, a random field Ising model. So you take the usual Ising Hamiltonian when the spins are plus minus 1, and you add to it eta v, which will be a Gaussian random variable independent for every vertex, which multiplies sigma v. So you give an a priori tendency to every vertex. Every vertex has, the spin wants to follow eta v. If eta v is 5, then the spin wants to be 1 with this strength. If eta v is minus 10, it wants to be minus 1 with this strength. And lambda controls the strengths of the disorder. A priori, this eta will be a Gaussian with variance 1, and multiplied by lambda, it has variance lambda squared. So this is again a somewhat standard setup. This is a random field that multiplies the spin, giving an a priori random tendency to every spin, either to plus 1 or to minus 1. And you can do something similar for the, say, random field Q state Potts model. Here, the spins take value, I remind, in 1 up to Q. They can take any value from 1 to Q. And if at position V, the spin takes the value K, then the energetic cost of that is eta Vk. That is, at every vertex, we have Q Gaussians. And if you take the value K, you get the K Gaussian. So you're trying to fit your Potts model in an environment of independent Gaussians. It wants to find the best sort of surface inside this environment. And again, the strength of the Gaussians is lambda. Or you can say differently, at every vertex, you have an a priori tendency to be either 1, 2, 3, 4, or 5 up to Q. So you may as well keep the Q equals 3 case in mind. So again, it's about a priori tendencies. You can also do something a bit different. The Edwards-Anderson spin-glass model means that for every bond, you have Ising variables, you have the Ising model, but the coupling of the Ising model is random. It's eta UV, so it's no longer ferromagnetic. For instance, some bonds want to be satisfied, some bonds want to be dissatisfied. You either gain or you gain eta UV, which would be negative if sigma U and sigma V agree, and you have a Gaussian for every bond. So this is the spin-glass model. And if you have a spin ON model, I remind the spin ON model, say the XY model, let's just think of that, means that the spins are in the unit circle in the XY model. Well, then you have a two-dimensional Gaussian at every vertex, which multiplies your spin. So it gives an a priori tendency on the unit circle. Okay, so this is the type of disorder I will consider, but I want to introduce this notation of F because it will come up later in the talk. So what I want to say is that I take the original Hamiltonian, and then at every vertex, I calculate F of the configuration around that vertex. TV is the translation by V. So it means you make V into the origin and you calculate F. So F is just going to be, say, the spin at the origin. Or maybe F is going to be the bonds that surround V. Or maybe F is going to be the indicator of whether you take the value K or not. And then you multiply that by the Gaussian. Lambda is the disorder strength, and that's the general formulation. So let me just emphasize that F returns a vector. It returns a vector of length M for some M. In the Ising model case, this is just a one-dimensional thing, sigma 0. But say if you're in a spin-glass situation, you need to have D bonds at every vertex. So you have D random variables for every vertex. Here you have Q random variables for every vertex. And here you have N random variables for every vertex. So M is the dimensionality of the quantity that you add the noise to. Okay, this is the setup that we will talk about. I hope it is clear. Please ask questions if it is not. And remember that F is going to be the observable that is noised, because F will come up in the talk. So F is the observable that the noise is applied to, that it is coupled to. Okay, so what do we want to do with this? So there is the well-known Imry Ma phenomena. Imry and Ma, they considered the effects of such a disorder for the random field Ising and the spin-ON model. And their prediction was that in low dimensions, even if you had a very small disorder, even arbitrarily small disorder strength will cause the models to lose their ordered phase. So you take the random field Ising model in 2 dimensions, and even the ground state will be disordered. So the addition of the disorder really changes the system a lot. It will, even the ground state will no longer be ordered. If you are in 2 dimensions in a general spin system, and if you are in 4 dimensions or less, when you possess continuous symmetry. This was on the physics level. And then Aizenman and Wehr, they proved this as part of a general statement. So we will now discuss the theorem of Aizenman and Wehr that proves the Imry-Ma phenomenon. So what does it say? Here is what it says. Take a disordered system as we just discussed and consider the spatially and thermally averaged observable. That is, you look in a big box at the average value of the observable, say the magnetization if you're in an Ising model. You look at the average value of the observable in the box, then the limit as the size of the box goes to infinity will exist and will take the same value for all the Gibbs measures of the model. And it will even be the same value regardless of the disorder. So for instance, you take the plus state of the disordered Ising model, of the random field Ising model, and the minus state of the random field Ising model, and they have the same magnetization value. This is, of course, surprising. Usually they're very different at low temperature, but this applies at every temperature. including zero temperature, including the ground state, and all of this in dimensions 1 and 2. But if you have a continuous symmetry, like in the spin-O(n) model, then it applies even up to dimension 4. This is what Aizenman and Wehr proved. This was the Imry and Ma phenomenon. Let me just say it again for the complete clarity. If you take the random field Ising model, then half of the spins will be 1 and half of the spins will be -1, regardless of your Gibbs state, of your boundary condition. And similarly, the Potts model, 1 over Q of the spins will be 1, 1 over Q of the spins will be 2, and so on. Every spin state will appear the same density of times, regardless of the Gibbs measure. And in the spin-O(n) model, the average direction on the sphere that you take will be 0. And all this regardless of the boundary conditions, and in these low dimensional systems. Okay, so this was done 30 years ago. And then what do we study? So our goal is to develop a quantitative understanding. So here we have a limiting statement. So roughly speaking, we want a rate of convergence in this statement. So we want to know that if you take a system which is finite but large, then in that system, the disorder will cause the system to lose the ordered phase. Okay, questions? So something quantitative about this.
Well, I have a question about Potts model.
Yes.
You are not saying anything about the transition at the transition temperature somehow.
I'm saying that there isn't any transition temperature if you're in dimension 2. Once you add the random field, so again, the random field says that at each vertex you have Q Gaussians, and they give you an a priori tendency on the Q states. I
understand that, but this is about, random field situation, but you need to have something like random temperature. There is a phase transition between low order and disorder.
So I'm saying that there will not be long range order. Once you add a disorder, even if the disorder has a very small strength, once you add it, you do not have an ordered phase anymore. You're all the time disordered in 2 dimensions. In particular, there is no transition, at least not in the usual sense.
Well, this transition is transition between the mean energy jumps. So for Potts model, you have a jump of mean energy, of the expected energy. And so you need to add something, to this energy, to this parameter. You are adding external field, so I understand this external field, but I'm talking about.
Okay, I see. You're talking about the different. So I'm not sure. The statement here only applies to the observable F, which means just the density of each spin state. I do not know indeed about the bond, but I would imagine that you're in the disordered state for any, in this case, for the Potts model, for any observable that you take. So even the mean energy, I would think, does not transition, but this is outside the scope of this theorem.
Yeah.
But it's a good question.
Okay.
All right. Okay, so I go on. So we want a quantitative understanding. Let's see the next slide. For the random field Ising model, a very special case, much is known now, but this is due to recent progress. So let's see. For the random field Ising, this was the case discussed here. Due to FKG inequalities, monotonicity, we know that the plus boundary conditions and the minus boundary condition induce the maximal and minimal boundary conditions. And then the Aizenman and Wehr theorem, which tells us that the magnetization is the same in plus and minus boundary conditions, will tell us that all the Gibbs measures coincide actually. So the model has a unique Gibbs measure. This is a stronger conclusion than what you get for general systems. And then you want to quantify this. So, okay, this was Aizenman and Wehr. Now we want to quantify this. And the natural way to do that, and this is the choice we take, is to consider the average magnetization in a finite box. So say the magnetization at 0 in a box of side length L. And if you're at high temperature or high disorder, then this is not a difficult thing to understand. And the average magnetization decays exponentially in the box size. But what is interesting is the case of small disorder strengths or low temperature. And these recent works in the last few years have shown better and better bounds on the magnetization by Chatterjee, myself, and Eisenmann. And then finally at zero temperature by Ding Xia, and at positive temperature by Ding Xia and Eisenmann, RL, and myself, it has finally been shown that the magnetization will decay exponentially fast in 2 dimensions. So you put plus boundary conditions, you look at the spin at the origin in the ground state. In the ground state, the spin at the origin is nearly half-half distributed. The deviation from being half-half distributed is exponentially small in the domain size. It's a very strong fact. The exact correlation lengths, C lambda, is not yet understood. The proof gives something pretty weak. Presumably, it will be quite large as the disorder strength is lowered. So maybe if you take disorder strength 0.1, you will not actually see it so much in an experiment with medium-sized system. Recently, Ding Wehr showed that it is at least this much. So this is the minimal scale, so you start to feel the disorder. It's not so clear if you feel it like in this manner, but at least this is the minimal scale to start to feel it. So for small disorder strength, you need to take a pretty large system. But okay, this is all about the random field Ising model, and my talk is actually exactly not on the random field Ising. What I would like to tell you about is when you go beyond the random field Ising, what can we say? And there are still interesting things, but we do not get the optimal results as yet. So I would like now to tell you about other models. So let's remind ourselves that we discussed the Potts model, the spin glass model, the spin-ON models. You cannot apply the analysis of the random field Ising model to them, mostly because they don't have the monotonicity properties, but also other features of the Ising model are important. So in fact, for the Ising model, what did we do? We bounded the magnetization under plus boundary conditions. What is the natural observable for a Potts model? It's not clear, because it is not clear that if you put constant boundary conditions, then this is what maximizes the chance to be this state at the origin. Maybe because of the random field, something else maximizes. So it is not even clear what is the quantity that you want, what do you want to quantify? But we have the following results. Let's look at the one main result. So we take a two-dimensional system, say the Potts model, and we look at the observable at the position V under the influence of boundary condition tau1. And then we look at the observable at the same position under the influence of a different boundary condition tau2. And we check whether they are the same or not. For the case of the Potts model, we're just checking, we're checking the density. What this is doing for the Potts model is checking the density of each state under this boundary condition and that boundary condition. And then we take the supremum over all possible boundary conditions, which may even depend on the disorder. So what we're saying is that you take the worst boundary condition, the one that gives you the maximal density of ones, say, and the ones that give you the maximal density of state 2, say. And even under the worst boundary conditions, the difference in the densities of ones and twos is not big. It's only this much in the system size. Now, this is not a very good quantitative estimate. Maybe one would really expect an exponential decay like in random field Ising, but it is what we get, and it is the first quantified result of the Aizenman and Wehr type. And it's uniform in the system. We get it for Potts, we get it for spin glasses, we get it in spin-ON, but for spin-ON we get something better, as I will explain. For spin glasses, it says the following: roughly half of the bonds will be for dissatisfied and half will be satisfied, and the deviation from half-half will be at most by this amount. This is what it says.
And if the disorder was not allowed to depend on, sorry, if a boundary condition was not allowed to depend on the disorder,
was allowed to depend on the disorder.
So I suppose you could hope to get better bounds, but can you conjecture a different result, or you expect to have the same result?
You mean if I fix the boundary condition and do not allow them to depend on disorder? That's what you're saying?
Well, I mean, if you take the supremum outside the expectation.
Yes, yes. So we don't know to get a significantly better result. Maybe, yeah, I think we don't get any better result for that. But it is natural to try. But let me mention that it is also natural to take the supremum inside, because that is roughly what the Aizenman and Wehr theorem is saying, that for every Gibbs measure, you have the same limit of this quantity. So we are comparing two Gibbs measures, two finite volume Gibbs measures, even the worst ones, even those that depend on the disorder. It's harder to place the supremum inside, and even that we can bound.
Thank you.
Yeah, we're happy with the supremum inside, actually. Okay, but here, actually, your question will become very relevant here. So here we have the d-dimensional random field spin-O(n) model. So it has the continuous symmetry. When you have continuous symmetry, the critical dimension goes up to 4. And here we are able to quantify the Aizenman and Wehr result in a better way. We can show that the expected magnetization, so you put boundary condition tau, and you look at the average direction that your spin is heading in the box. And we can show that this expectation tends to 0 in dimensions 2, 3, and 4, like a power of L of the system size in dimension 2 and 3. And we have only a log-log upper bound in dimension 4. So here, let me just mention that at first sight, because the critical dimension for the disorder to be relevant is 4, so this is actually conjectured. It's not known that in 5 dimensions it is not relevant, but it's conjecture. Let me just say that you might expect, because dimension 2 and 3 are subcritical, that the correct decay rate should be exponential, like in the random field Ising model that the decay rate was exponentially fast in L. Let me just mention that there is no consensus on that in the physics literature. Some physicists predict that in dimension 3, the correct decay rate will be a power for small disorder strength and low temperature. So there will be some kind of Berezinski-Kosterlitz-Thouless transition that at strong disorder, the decay is exponentially fast, and at weak disorder, the decay is only power low fast in dimension 3. That would be very interesting. If that is the case, then this is an optimal result in the sense of a power law, but not the optimal power, probably. So for instance, Gingras and Huss and Feldman, if I'm not mistaken, wrote about that. Although there were other works as well, Tarius and yeah, I don't have the names in front of me now, but there were also other works that thought that maybe there is no such transition. So it's not clear. Okay, so these are our results. And I will also tell you, as I said, about non-compact spins, but perhaps at this point, there is still something I want to tell you, but then I want to explain an element of the proof. In a previous version of this talk, I discussed the proof of this fact. So in this version of the talk, I will discuss something about this fact. And you can see the previous version on my website. So if you're interested in the sketch of proofs of both facts, this will give you a more complete picture. Okay, but before I enter into that, let me also state a qualitative feature. So again, Aizenman and Wehr gave us a qualitative result. They told us that this kind of limit, the average magnetization, is the same for all Gibbs measures. We are giving a quantitative result that says that actually the deviation is at most like that in the system size. But let me add another qualitative result to the fray here. So let me just state it here in this form. So we are thinking that in fact, let me mention, you cannot expect a unique Gibbs measure in 2 dimensions always. So you might expect maybe there's just a single Gibbs measure. This you cannot expect, because if you take a spin glass system, you take a ground state, you can always flip all of the spins, apply minus to all of the spins, and the energy will remain the same. So obviously, if there's one ground state, there is also a second one. There's no uniqueness in general. But what we conjecture is that there is uniqueness of the observable. That is, you should think of this as the observable at 0. You take a big box, then the observable at 0, averaged, thermally averaged over the temperature, over the Gibbs measure with respect to the temperature, this will take the same value for all boundary conditions. So in the Aizenman and Wehr result, we had something similar, but you had to average over this space. You had to average over the box, and here you do not average over the box. We believe that even that will occur. If this is true, then it will imply the well-known conjecture that spin glass, Edwards-Anderson spin glasses in 2 dimensions have a unique ground state pair. So this is a stronger conjecture. And I don't want to take a lot of time on this, so let me just add that we can do something partial in this direction. Without going into the definitions, I will just say that we can show that such thermal averages will be the same for all the translation covariant Gibbs measures. So it's a partial result. And there is some subtlety here that we don't know that the translation covariant Gibbs measures are supported. If you're at 0 temperature, that they're supported on a unique ground state. We don't know that. So it's not quite the same as what you might want for a spin glass, but in any case, it's a partial result that there is a unique average over translation covariant Gibbs measures. Okay, so, but I don't want to enter this. The difference from Aizenman and Wehr is that you don't need to spatially average, but I don't want to enter into this. So now I want to tell you something about the proofs. And again, in a previous version of the proof, I sketched of the talk, I sketched this kind of result that applied to general spin systems. I'll just show this for the people in the video, but you can also see it on my website. But in this version of the talk, I want to sketch for you a different proof. So, okay, what I want to sketch for you is the proof that we have for the random field XY model. So for the random field XY, I remind you what we can show is that you take the average magnetization, and even in the supremum over boundary condition, it decays like a power law in 2 and 3 dimensions. I will show something a bit weaker than that. I will do what Daniel said. I will take a fixed boundary condition instead. But actually, the main ideas are already there, and it's actually not complicated as well, which is nice. That way people can understand. So let me stop my share. Okay, let me stop my share and share from my tablet and show you something about the proof. All right, just a minute while I get this organized. Okay. So maybe I will also give you some intuition, and this intuition will be relevant for my later explanation. Why would we expect the Imry and Ma phenomenon? What is the heuristic of Imry and Ma? Maybe it's not exactly what they said, but this is the idea. So why would low-dimensional spin systems lose their magnetization and their ordered phase in low dimensions? So say the Ising model. So consider, say, the Ising model. If you believe that you still have an ordered phase when you add the random field, so random field Ising, I should say. If you believe that you still have an ordered phase, then probably you also believe the following. Consider a box of side lengths L and put plus boundary conditions to this box. If you believe that there is still magnetization, then you probably believe that the energy of the full plus configuration is better than the energy of is smaller than the energy of the full minus configuration. Let me again just remind the Hamiltonian. The Hamiltonian is the sum over all nearest neighbors of this usual Ising factor. All right, just with the signs. Okay, and then we add to that a disorder in this manner. And the eta V are IID independent, identically distributed Gaussian random variables. So, okay, so what is the energy? Energy of fully plus configuration minus the energy of the fully minus configuration with this boundary condition, with plus boundary conditions. So you get a contribution from two terms. First, you need to take into account the nearest neighbor coupling. Obviously, they will have the same nearest neighbor coupling except on the boundary. For the boundary, you get something of the boundary size. So obviously, the fully plus, maybe, okay, the fully plus configuration will have a lower energy with some constant L to the D minus 1. So this is the boundary contribution. Okay, but this is not everything you need to take into account. The other thing you need to take into account is the disorder. So with the fully plus configuration, you get the sum of the eta V's. And with the fully minus configuration, you get minus the sum of the eta V's. Now, what is the order of magnitude of the sum of the eta V? When I sum all of the Gaussians in the box, in the volume, how big is that? Don't be shy.
Like the square root of the volume?
That's right. That's the square root. Right, so the sum of them is normal, 0, and variance L to the D, as we all know. So this means that you get an additional contribution of lambda L to the D over 2 times the normal 0, 1. So this is what you will have. And if you think that the fully plus configuration is favored over fully minus, then you think that this term is more negative than what this term is positive. So you ask yourself, is it favored? So is this positive or negative? Is this negative, you can ask. And the answer is yes, in dimensions greater or equal to 3. But in dimension 1 and 2, you see that actually this factor L to the D over 2 can overwhelm this L to the D minus 1. In dimension 2, it's exactly critical. They have the same order of magnitude. But because of the normal 0, 1 factor, it can go beyond the constant. So it is possible to do it with reasonable probability. And then if you look at increasing volumes, you look at larger and larger volumes, there will be some volume where the sum of the eta V, where this factor overwhelms this and causes a disconnection from the boundary. So this roughly is the heuristic of Imry and Ma, that in dimension 2 and 1, you can overwhelm it, and it will happen for some volume. So no, in some volume, in some domain, in some large domain, in dimensions 1 and 2.
Why you are always mentioning dimension 1?
Well, dimension 1 is not so interesting for the random field, is it? But actually the phenomena is more widespread. We consider only the nearest neighbor case, but Aizenman and Wehr considered more general systems with long range interactions as well.
Okay.
And if you consider this, then it's interesting to discuss. But you're right, you're right. Although, I mean, it's obvious that it shouldn't help you, the random field, but mathematically speaking, sometimes it's hard to prove. So, okay, so it's also true in dimension 1. And what happens when you talk about the random field XY, and actually this will be related to what I will say very soon. And so for the random field XY, you can try a similar analysis. So now the spins are on the unit circle, and let's say they all point in this direction. So I remind that sigma at every point belongs to S1, the unit circle. And then the Hamiltonian is exactly very similar to the Ising case. So minus, maybe I write like this, it's some U adjacent V, sigma U minus sigma V, norm squared, minus lambda sum over V at the V times sigma V. Okay, so now the point is to consider a volume of half the size. So this was L, and inside it, I consider a box of half the size, like this, L over 2. And I consider the two possibilities there. What will happen if I place, what is the difference of energies between the fully facing this direction configuration in lambda L over 2. So this is lambda L over 2, okay? And the fully facing in the other direction configuration. So you can ask, what is the difference of energies, just like we did for the Ising model. And the point is that because of the continuous symmetry, you still need to prove that the surface tension, the gain in energy or the loss in energy, when you pass from these boundary conditions to the opposite boundary conditions, after a distance of L over 2 or L, the loss in energy, you don't need to form a domain wall. You can rotate the spins very slightly, and you hope that the difference in energy will be of a lower order of magnitude, will not be L to the D minus 1, but only L to the D minus 2. And this is what Aizenman and Wehr were doing rigorously. So the boundary contribution reduces to L to the D minus 2 due to the continuous symmetry. But this needs to be explained because there is a random field, and the random field obviously breaks the symmetry. So this needs to be explained. Okay, but this was the heuristics behind this, and Aizenman and Wehr made this precise. Any questions about the heuristics? Okay, so what we are showing, theorem, this is not only for the random field Ising, this is for any spin ON, but I'll only discuss the random field XY, sorry, the random field XY. So for the spin ON, n greater or equal to random field spin ON, model in dimensions D equal 1, 2, 3, and 4. Sorry, Roman, for including 1. Then we can show that for any L greater or equal 1 and any fixed, but we can do more than fixed, but for now I talk about fixed, and any fixed boundary condition tau, the expected magnetization, so you take the norm of 1 over L to the D, sum V in lambda L over 2, spatial average of sigma V under the Gibbs measure with boundary condition tau in the volume lambda L. So we take a half-sized box. This is smaller or equal to 1 over L. Okay, let me not include dimension 1 because I don't remember what it gives. It's not so interesting. So this is 1 over L in dimension 2, 1 over root L in dimension 3, and 1 over root log L in dimension 4. This is our result. It's different from the results in the slides because in the results in the slide, we didn't have a fixed boundary condition. We had a supremum. If you add the supremum, then the powers become a bit worse, but the general idea stays. So instead of these powers, you have worse powers, but the general idea is still there. So I don't explain this point. Let me give you the idea of proof. So fix n equal to 2 and discuss only the ground state. So we only talk about the random field XY model and only the ground state, because that will already give you the idea. So fix the boundary conditions tau, as we explained. Boundary conditions tau. And the right write E, L, tau, and the eta for the energy of the ground state. Maybe I'll give a name. The ground state, I'll call it the ground state sigma. Sigma L, tau, and eta. Eta is the random field. Energy of the ground state in this volume, in lambda L. Okay, then the bound is based on the following. Given eta, define eta tilde to be something very similar. Eta tilde is eta v when v is not in the half-sized box, and it's minus eta v when v is in the half-sized box. So again, we take the box of size L. This is where we work in. Inside this, we identify the half-sized box, lambda L over 2, and we are reversing the direction of the random field inside. And this we call eta tilde. And then what we care about is the difference of energy. So the main quantity, and this is also a quantity that was considered by Aizenman and Wehr, and in some sense we're following the footsteps that they started. So we consider EL tau eta minus EL tau eta tilde. So the question is, maybe I call this quantity G. The question is, when you reverse the field in the half-sized box, what is the effect on the ground state energy? And then the basic claim that we prove is that this effect is not that big. So claim the expected G, and even given, and this is important, given eta in the half-sized box. So just to clarify, this means conditioned or for fixed eta in lambda L over 2. This is what I mean by this conditioning. This difference of energies is at most some constant divided, okay, if I use the previous notation, a constant L to the D minus 2. So this is leading us back to the previous heuristics. We were saying that the boundary contribution in the Ising model is of size L to the D minus 1, but the boundary contribution in an L to the D minus, in the XY model should only be L to the D minus 2. So actually the claim that I'm making now is of that flavor. I'm saying that if you take two different fields in the half-sized box and with the same boundary condition outside, then the difference in the ground state energies on average, but fixing the half-sized box, is only of this magnitude. So it is like in the heuristics. And what is the idea behind that? So I remind the sigma L tau eta is ground state in lambda L. The idea is that we can rotate it slowly. So the usual spin wave that you probably are familiar with, can rotate it slowly between lambda L and lambda L over 2 so that it is reversed on lambda L over 2, and at the same time rotate the random field, the random field eta there. Okay, so let me try to explain with the picture what I mean. So I have the full, make it even bigger. I have the full box and the half-sized box. And what I do, I take the ground state and I apply a uniform rotation. So initially the ground state was like this and like that and like this. I don't know what it was exactly. It was something. And I'm going to apply a uniform rotation. So this is slightly rotated to the left, and this is slightly rotated, slightly rotated, slightly rotated, until when I'm inside, I gain a full rotation. What was this becomes that. Okay, I just uniformly rotate it. Uniform rotation, and I apply the same rotation to the field. So what is the effect of this rotation on the energy? Because the energy takes this form, because I rotate both eta and sigma, then the dot product remains the same. The only effect is in this term. In this term, it's a bit hard to say. I had two spins next to each other. I rotated both, but I didn't rotate them in the same amount. So I'm rotating more and more as I go to the center because I want to achieve the uniform rotation inside. Yeah, actually my picture doesn't quite explain that. So let me do the picture a bit better. I'm rotating more and more as I go inside until I get the uniform rotation. But if I average, by averaging the rotation clockwise and anti-clockwise, so I consider both possibilities of the way to rotate this, the average energy difference, is only of order 1/L squared per bond. So this is a usual trick, Mermin-Wagner, if you will. So the usual spin wave, if you will. So let me just put these words, Mermin-Wagner or spin wave. And okay, and I hope I gave you some hint of what is entering this. It's not a difficult statement. It's a relatively simple statement. So, and this will prove what is stated here. Okay, maybe you need to think a little to see it, but I just want to give a sketch. So this is proving what is written here. Okay.
So Ron, so are you flipping the random field only inside this half box, right? You're not rotating.
Yes, okay, that's right. In the half box, I'm flipping it, and in the here, I'm using the fact that I'm averaging over the random field and the fact that the random field has a rotationally invariant distribution.
Okay. So you're rotating random field.
If I rotate the field as well. But this is due to the fact that I'm averaging over it, but I'm not averaging over the middle box. I'm fixing it in the middle box. I'm only averaging it in the annulus.
Oh, okay.
And I'm using that it has rotationally invariant distribution.
Okay, that's clear. Thank you. So you can use this harmonic analysis type. Okay,
yes,
thanks.
so it's not a difficult fact. And once we have it, now consider, so this I put here, end of sketch. Now consider the derivative of G, not of G, of this expectation, of the expectation of G with respect to eta lambda L over 2, with respect to the average field eta hat L over 2, which is the average of eta in the box of size L over 2. Okay, so this takes a little while to digest. So let's see this. So what is G? Let's recall what is G. So G was the difference of energies between taking the field in one way or the opposite way in the half-sized box. When I take an energy like that and I differentiate it with respect to the average field, then that's actually a pretty simple expression, although one has to make sure to think, but it's actually a simple expression. What I can do, when I change the field, when I change eta, the energy changes by sigma, basically. If I differentiate by the average of the eta, I will actually get the sum of the sigmas. The average of the eta multiplies the sum of the sigmas. So what will actually happen when I take this derivative is that I will get the sum of the sigmas for the configuration with this eta, for this ground state, and the sum of the sigmas for the other ground state. One has to think a little about that. It's not completely obvious, but it does follow. And it's really because of the way the energy is written. So actually the derivative of this will be the difference in the magnetization between the ground state here and the ground state here. It's just that. One has to think a little, but it's not complicated. So the derivative of this is the following: to get the sum over the half-sized box of the ground state sigma L eta tau at V minus sigma L eta tau tilde at V. So it's exactly the difference of the magnetizations. Okay, and now with this difference of magnetizations, what do I know? So let's call this, okay, but I was taking the derivative of the expectation. So the expectation stays. So I still get the expectation of that conditioned on eta lambda L over 2. And let's call this G prime. Okay, this will be my name for this expression, G prime. And notice G prime is almost what I want. But importantly, sorry, there was something very important I forgot. Because tau tilde is reversed with respect to tau in the half-sized box, this minus now becomes a plus. Okay, because it's multiplying the opposite field. So
isn't tau the boundary condition? What? I'm confused.
Sorry, not tau, you're right, it's eta.
You want to say eta tilde?
I want to say eta tilde. Thanks a lot. I made the mistake here. Thanks for catching it. I also switched the locations of tau and eta from my previous notation. Sorry about that. Very good. Okay, so in conclusion, sorry for going a bit fast. This expectation equals, now I'm taking an expectation also over the field inside. And if I take this further expectation, then these two terms are exactly the same in distribution. So I will get twice the expected sum V in lambda L over 2 and the ground state magnetization, sigma L tau eta V. And this is the quantity I would like to control. I remind you, the theorem says that this expectation is not too big. Maybe I'll just flash the theorem. The theorem is also at positive temperature, but in particular in the ground state, it says that this kind of expectation, when averaged over the volume, is not big. So this is what I want to bound. So what remains? Not much. So, okay. We want to bound G prime, which is the average, the expect. Okay, we want to bound G prime. We know that G is less than or equal C times L to the D minus 2 uniformly in the random field eta. We want to bound the expected G prime. Okay, so we have some function G. It's uniformly bounded. Let's try to make a plot. This is G. On this axis, I put eta hat lambda eta hat L over 2. I have a function. I don't know much about it, but it's uniformly bounded, so it's never above this line. It's never above C L to the D over 2. And then I ask myself, and actually we also know it from the other side. It's obviously symmetric. I did it in one side, but I shouldn't have called this G and G prime. It's, sorry, this is what I want to call G. So this, sorry about that. Okay, this is what I want to call G. And so we have a function that's uniformly bounded. And actually also from below, because there is some symmetry there. So it never goes beyond the CL to the D over 2 or below this. So D minus 2. So I don't know what it does. Maybe it's like this, maybe it's like that, could be a lot of things. And what we care about is to take the derivative of this function with respect to this variable and to average it. And what matters is that this variable has quite large fluctuations. The fluctuations of, oh, sorry, some problem here with the tablet. The fluctuations of eta hat L over 2 are of order L to the D over 2. Well, okay, the way I've written it, L to the minus D over 2. And maybe then it would be better to talk about 1 over the volume, 1 over L to the D times G. And sorry, let me put here 1 over L to the D times G. And then this is at most CL to the minus 2 and CL to the minus 2 here. Okay, so now there comes just a simple fact. You have a function, you're averaging it over a big range, you're averaging it over this range, you're averaging the derivative over a huge range. you cannot always have a big slope. If you had a big slope always, if the derivative was always big, then it would contradict the fact that it's bounded above. You're averaging it over a huge range. If the slope, if the derivative was always big, then it would contradict this upper bound. So actually the average of the slope must be a bit small. The average, so the conclusion is that the average slope of 1 over L to the D times G is not too large. The order of it is at most the ratio between these two quantities, the upper bound and the thing that the range that we're averaging on. So it will become at most C L to the D over 2 divided by L squared. And this is what we were discussing in the beginning, 1 over L in dimension 2, 1 over root L in dimension 3, and this will only give us a constant order in dimension 4. This is the idea of the proof. In dimension 4, you have to go a bit further, but I won't go into that. In dimension 4, we augment this analysis, by a Mandelbrot Percolation analysis, but I won't go into that. It's not a complicated thing, but I don't want to have the time. So by Mandelbrot Percolation, I roughly mean that you divide your box into many small boxes, and you apply this idea separately on the small boxes and ever smaller boxes, and somehow iteratively, recursively. Let me not go into that. Okay, this was the idea. Sorry, I hope you could get something. This quantity that we care about is bounded, and you're averaging it over a big range. So the slope of it cannot be big, but what you want to bound is the average slope. So you get your bound. Okay, this is the idea. It's really not complicated, but it's still hard to convey like that. Are there questions?
Yes.
Yes, so please ask, yes.
Yeah, so this is beautiful. But so by this argument, you got this upper bound 1 over L or 1 over square root L. So are these regarded to be optimal, or do physicists imagine, do physicists believe? Yeah, power.
So I would.
Yeah, this power, yeah, 1 over L, yeah.
I'm guessing that in 2 dimensions, you actually have exponential decay, because seems somehow really a low dimension. Even the random field Ising has exponential decay, and XY should fluctuate, I imagine, even less.
Even in 0 temperature.
Even at 0 temperature, the random field is exponential decay of correlations, even at 0 temperature, yes. So I would imagine this. But in dimension 3, there is no consensus in the physics literature whether we expect exponential decay or power law decay. And definitely people don't know the power. So it is, I mean, there is no reason to conjecture that this is the correct power. But the more basic question is even if there is a power or whether it's exponential decay. For instance, Gingras and Hughes were arguing that there is power law decay. And this would be a position because there's definitely exponential decay at strong disorder. So it means that at low temperature and weak disorder, you have power law. It will be a sort of Berezhinsky-Kosterlitz-Thouless transition.
Okay. Okay, so this means that this picture, this graph of G over L to the D is not something optimal. Okay, so there's some different physical mechanism that determines the slope of G.
It's quite possible, yes. At high temperature and strong disorder, there is exponential decay due to more simple mechanisms. Low temperature and weak disorder, no other mechanism is known. But indeed, the optimal power, I don't know what it is.
Okay.
Gingras and Hughes do have do give a theory, so I shouldn't say not known, but no consensus. Are there other questions?
Perhaps any chance to also look at the model with disorder on the interactions rather than.
So this is included. So when you put the disorder on the interactions, as we have for the spin glass model here, you mean specifically for the continuous spin interaction or in general? If you disorder interactions for spin glass, for
yes.
spin sake, this is included in the analysis, and we get that the correlations decay at least as fast as a power of log-log. So it means that for spin glass, say, that roughly half of the bonds will be satisfied and half dissatisfied, and the deviation from half will be at most this much in the system size uniformly over all boundary conditions. So we allow to put the disorder everywhere you want, actually. But it must multiply something, and the observable that it multiplies, this is F. So this is the observable for which we can say something, what the disorder multiplies.
And if you put the disorder in both the interactions and the magnetic field?
Then, yeah, then it's, I mean, say you give this one a Gaussian and this one a Gaussian, then you get both. You get this much deviation for what the first Gaussian multiplies and this much deviation for what the other Gaussian multiplies. So yeah, whatever noise multiplies, each of the quantities it multiplies has this much deviation from the limiting value in uniformly over boundary conditions.
And then you get the same dependence on the dimension. It's not like increasing the dimension one more.
This is in the two-dimensional scenario. We can only add higher dimensions if you have a continuous symmetry. Then when you have continuous symmetry, I don't know, yeah, you might be able to do it with some bond, but I'm not sure about that. So for the higher dimensional thing, we only consider something like the Spinowhen model. So we don't noise the random field Spinowhen. So we don't noise the interruption. Not clear that for that. You saw the argument. This Norman-Wagner rotation is what might fail if you have a different noise. And indeed, it may be that they're not noisy in higher dimensions, only in 2D. I mean, the disorder might only be relevant in 2D for such a system. This I don't know.
Thanks.
Sure. So I actually wanted to tell you a bit more, but I'm out of time. So it depends on whether I have a few minutes or not.
Time is up, but
yes, okay.
Maybe you can. I mean,
I'll just flash something. I won't enter into any details, but I'll flash it. So let me say that we also have results about non-compact spin state when the spin state values in R or in Z. So this is when you talk about a random surface of the gradient type. So you say the Gaussian free field, but you add to the Gaussian free field a random field, eta multiplying the height. This is sometimes called the random rod model in physics literature. And we also have results when it takes integer values, and we care about the localization and delocalization properties. And the interesting result is that this type of surface delocalizes all the way to dimension 4 when it takes real values. So this idea that you lose the ordered phase up to dimension 4 in the presence of continuous symmetry applies also for height functions and causes delocalization up to dimension 4. Here we get the optimal powers, optimal dependency. And we also care about the integer valued case, and there the results are less complete. We can show it delocalizes in dimension 1, 2, and that it doesn't delocalize in dimension 3 if you have weak disorder, but we think that it undergoes a roughening transition, that in dimensions 3 and 4, it will delocalize like the real valued field when the disorder strength is raised. So I don't have the time to look at that, but I just mentioned we have real valued random field Gaussian free field and integer valued random field Gaussian free field. And we're trying to understand a roughening transition, possible roughening transition dimension 3. We don't know how to do it, but we conjecture it exists. And these types of setups have been looked at by Bovye-Kulske, Kulske-Orlandi, Van Enter-Kulske, Kotarin-Kulske. All of these works have Kulske in common. But we have new results. In particular, the integer valued random field Gaussian free field, we're probably the first to look at. Okay, so that's it. Here are the open questions. To improve the decay rate, 1/log is probably not optimal, it's probably exponentially fast. To prove the uniqueness conjecture, to understand if in dimension 3, the correct rate for XY model is really a power law or not, is there a Brzezinski-Kosterlitz-Thouless, and to understand whether there is a roughening transition for the integer valued random field Gaussian free field. These are the main questions. Thank you very much, and sorry for going over.
Thank you very much, Ron, for this very nice and very clear presentation. Do we have questions from the audience? So actually, I have one, or maybe you said it and I missed it. So, but so
yes.
Does the method also allow to get insight on, let's say, disorders in spin correlations, or like averages of products of spins that are far away from each other?
Yes. So, for instance, in the random field Ising, this was made explicit in what we wrote with Michael Eizenmann, probably was known before too, that if you control the magnetization under any boundary condition, then this is in some sense even stronger than a spin-spin correlation, because no matter what you put outside the box, you know that you're not affected by that. So this is stronger than a spin-spin correlation. The upshot is that if you control this type of observable, then you also control a disordered spin-spin. I don't know what would be the analog of that for a general system. So if you're in a Potts model, I'm not sure if you actually get this decay rate for spin-spin. Maybe you do for a Potts model, but not for spin glass. It depends a little on your setup.
Mm-hmm.
So it has the flavor in any case. You're saying that the boundary condition cannot affect you too much. So it has the flavor of the decay of correlation.
And does this apply also to random bond Ising, or that you were mentioning random field, I guess?
So yes, it applies, but in this type of way. So for random bond Ising, it means that F will be the energy of the bond. Mm-hmm. What this will tell you is that the spatially and thermally averaged energy of a bond is the same in all the Gibbs states up to this type of, in a finite volume, up to this deviation at most. Mm-hmm. So you can apply this. The way the disorder enters was very general. We allow quite a lot of possibilities. It multiplies some quantity in the Hamiltonian, and that is the quantity for which you get, you see it multiplies eta, multiplies an F, and this F is what you get the correlation decay for.
Okay, thanks.
Sure, thanks for the question.
Other questions? So I guess in the heuristics of Imry and Ma, in the critical cases, they had some renormalization group argument, like...
No, I mean, at least not in the heuristics I presented. It was much easier than that. You mean the critical dimension, right?
Right, yes. I mean, the very first heuristic you gave us, a d equal to, there's a, I mean, a d equal to, you cannot say who's bigger than who, right? So...
That's right, but let me explain the following point, that this is a normal 0-1 random variable, which is obtained by summing all of these. So in a given volume, you take the sum of all the etas of the noise in a box, and either it's big or it's not. Suppose it was not big, so that in fact the boundary contribution 1. Then you just take a twice bigger volume and try again. And for twice bigger volume, you have almost independent eta. They include the etas that you had before, but mostly they're new eta. So you try again, maybe it works. If not, you take twice bigger volume, you try again. Eventually, you will come across a box where this normal 0-1 variable is larger than 1 over the disorder strength times this constant C and overwhelms the boundary contribution. Hence, heuristically, there will be boxes which disconnect you from the boundary. And once you reach such a box, it doesn't matter if your actual boundary condition is even further away because it cannot go in that box.
Mm-hmm.
So this was the heuristic why in the critical dimension you still win, because you will win in some box, and after you have some box, you win anyway.
Okay, thanks.
It's because this is uniformly bounded and this is random. That's the basic point.
Okay. Okay, thank you. Sorry, but maybe there were other questions from the audience. Okay, doesn't seem to be the case. So thanks again to Ron for the very nice presentation. And we can stop the recording.